Hello and welcome. My name is Amanda Lowe and my partners here are Travis Euler and Shashank Jitendra-Sinha, and we are the Deep Sea RTG group. So first off, what is an RTG? An RTG stands for radioisotope thermoelectric generator. These are devices capable of converting heat from a decaying radioisotope, such as plutonium, and converting it into electricity. They're meant for remote, long-term power generation where it's not easy to recharge a battery or have access to the grid. As part of this, they naturally have a very passive design and require very little maintenance. Because radioisotopes generate heat as they decay, an RTG can also provide usable heat for various applications. Adding on to that, here is some background on key components such as thermoelectric generators. These are essentially many thermocouples placed in series in order to generate a voltage at a usable scale. And a thermocouple being a wire made up of two different conductive metals attached to each other and will generate a small voltage when a temperature difference is applied across them. Not very efficient, but it's a passive device that can generate electricity. Some notes on the radioisotope to be used, as not all radioisotopes produce enough heat. The shorter the half-life, the more energy it emits, but it also has to be long enough to provide a long service life, and the type of radiation emitted has to be easy to design around. Here are also some further notes on shielding and heat conduction, but not as important as the previous two. So some historical and current day applications. RTGs were invented in 1954 by Kenneth C. Jordan and John Burden at Monsanto's Mound Laboratory. NASA has notably used these for remote-powered spacecraft, and the USSR has deployed these to remote lighthouses as well.
So based on the previous slide, we realized that RTG is already a well-developed application used in space currently, and we noticed that we could leverage the RTG and use it in underwater applications since it is currently being used in underwater applications. The primary reasons for that were underwater sensors like tsunami sensors, earthquake sensors are extremely important and are at the forefront of keeping our economy safe from natural disasters. But however, they are like in environments that are hard to reach and powered by lithium-ion batteries that need continuous replacement. So an RTG would help reduce maintenance costs by reducing the amount of times you need to replace the battery, perhaps 1 in 10 years, 1 in 20 years, depending on the amount of fuel we use, and additionally reduce maneuverability required, reducing costs as well. So this slide highlights the list of our deep sea competitors, and all of them are essentially conventional lithium-ion batteries with a few alkaline D-cell and lithium polymer battery systems being used. And it highlights that our benefit that it would be lighter, would be able to generate more power in theory, and would require no recharge and no battery maintenance, in addition to less weight and less maintenance. So our current competition would be current lithium-ion batteries and lithium polymer batteries that have a lifetime range of ranging from 10 years to 25 years, depending on the size and usage. However, the main issue with these batteries, as previously mentioned before, is they need constant recharge every 6 months to a year, which our RTG doesn't require, since it would run till the end of the lifespan, since it primarily uses radioactive fuel source strontium 90 from strontium nitrate as its heat source. Additionally, the cold environment from the ocean around it would create a big temperature difference, and we would be able to use that temperature difference to generate extra electricity using thermoelectric generators. So the main components of our design is the steel container that holds the device and also acts as a pressure valve. The aluminum block would block the electronics and the electronics of the device from the beta radiation from strontium 90 that rests on top of the thermoelectric generators, which are on the hot side. We would have 2 to 4 heaters of 20 watts each to simulate heat from strontium 90, since we weren't able to obtain the fuel source. So this is out of our budget constraint of $450. And additionally, we added thermoelectric generators under the aluminum block to create electrical output. The aluminum disc at the bottom acts as a cord side to our heat.
Here's a quick inside view into our device. At the bottom we have the aluminum heatsink, and on top of it the thermoelectric generators. Then on top of the thermoelectric generators, we have our aluminum container for the strontium-90 compound. And then around that, we have the heaters inside and the thermal insulation on the outside, as seen below. So some metrics found, that being highest internal temperature being about 100 to 120 C, average temperature difference being around 30 degrees across the tag, and peak voltage generated is 5 volts and about 1 watt of power.
We have performed many tests to determine how our system behaves over time. This includes plotting the temperature at various positions as well as the voltage produced. Temperature decay and strontium-90 mass decay have been correlated to determine how the simulation time relates to the real system time. Finally, various load lines have been performed to determine the power output in different environments.
So as you can see here, we have our setup with the ice water acting as the seawater, our hot internal components, and the vessel around them. As you can see, we have LEDs being powered currently from the temperature difference, as shown here on this display screen we have set up with the microcontroller. The power is currently off, so we're running off of residual heat, and which we'll just switch the load here to demonstrate the power being generated by spinning this fan. We also have the Arduino running to measure voltage and power. So currently we have the top value and voltage, and we'll switch over here to get the power in watts. So 0.6 to 0.4 due to the heat dissipation currently.